This is SpaceTime, Series 23, Episode 19. Coming up on SpaceTime, rocking and rolling on the red planet Mars, understanding the birth of atoms, and Earth's new second moon. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New data has revealed that Mars is very geologically active, with regular marsquakes occurring across the red planet. These are among the many findings from NASA's Mars InSight lander, reported in 6 papers published in the journals Nature Geoscience and Nature Communications. So far, more than 450 marsquakes have been recorded by InSight. The largest reached a magnitude 4. Here's what they sounded like, sped up so you could hear them. The findings are based on scientific data recordings captured by InSight, which arrived on the red planet's surface on November 26, 2018. The lander touched down on the Elysium Planitia, a broad expanse that straddles the Martian equator, just south of the Elysium Volcanic province, the second largest volcanic region on the planet after Tharsis. Among the reports is data examining some 174 seismic events over a period of 235 Martian days. That's from roughly a month after the lander touched down on the Martian surface through to September last year. Scientists say the findings suggest the red planet has a moderate level of seismic activity, roughly intermediate between that of the Earth and the Moon. The data's come from InSight's seismic experiment for interior structure, and it's provided the first direct seismic measurements of the Martian subsurface and upper crust, the rocky outermost layer of the planet. One of the study's authors, Nicholas Shermer from the University of Maryland, says InSight's the first mission focusing on taking direct geophysical measurements of any planet besides the Earth, and it's provided the first real understanding of the Martian interior structure and geological processes. The findings will help science better understand how the planet works, its rate of seismicity, how active it is, and where it's active. Of those 174 quakes InSight measured, 150 were high-frequency events that produced ground shaking very similar to what was recorded on the Moon during the Apollo program. The waveforms showed small magnitudes and shallow hypercentral depth, bouncing around as they travelled through the heterogeneous and fractured Martian crust. The other 24 quakes were predominantly low-frequency events with magnitudes between 3 and 4. 3 showed distinct wave patterns similar to quakes on Earth caused by the movement of tectonic plates. These low-frequency events allow scientists to extract information about subsurface structures. Based on how the different waves propagate through the crust, the authors can identify geologic layers within the planet and determine the distance and location to the epicenter. The researchers identified the source location and magnitude of 3 of the low-frequency marsquakes and believe that 10 more are strong enough to eventually reveal their source and magnitude once analysed. Understanding these processes is all part of a bigger question about the red planet itself. Can Mars support life, or did it ever? We know that here on Earth, life can exist at the very edge where equilibrium is cut off. Just think of areas like the hydrothermal vents along the deep ocean ridges, where chemistry provides the energy for life rather than the sun. If it turns out there's liquid magma on Mars and we can pinpoint where the planet's most geologically active, it might well guide future missions searching for the potential for life. Now, as we discussed last week, detecting signs of life was the primary mission for the earlier Mars probes Viking 1 and 2, and each of the landers carried a seismometer. Problem is, they were mounted directly on the landers and provided no real useful information. In fact, the Viking 1 instrument didn't even unlock properly, and the Viking 2 seismometer only picked up noise from wind buffeting the lander. There were simply no convincing marsquake signals. But the InSight mission is dedicated specifically to geophysical exploration, so engineers have worked to solve the previous noise problems. To do this, a robotic arm on the lander placed the seismometer directly on the Martian ground and some distance away in order to isolate it from the spacecraft. The instrument was also housed in a vacuum chamber, and the whole thing was covered in a wind and thermal shield. InSight's seismometer is sensitive enough to discern very faint ground vibrations, which on Mars are 500 times quieter than ground vibrations found in the quietest locations on Earth. The seismometers also provided important information about the Martian weather. Low-pressure systems and swirling columns of wind and dust called dust devils lift the ground just enough for the seismometer to register a tilt in the substrate. And high winds blowing across the surface of the ground also create a distinct seismic signature. Now, when combined with data from meteorological instruments aboard the spacecraft, the seismometer data helps paint a picture of the daily cycles of surface activity in the area. InSight landed on a thin sandy layer reaching a few metres deep in the middle of a 20-metre wide ancient impact crater in an area with strong winds and temperatures ranging from 0 degrees Celsius down to minus 80 degrees. The data also indicates that at greater depths, the Martian crust has properties comparable with Earth's crystalline massives, but on the red planet, it's all far more fractured. The propagation of the seismic waves suggests that the upper mantle has a stronger attenuation compared to the lower mantle. And even though the local air pressure is only 1/99th that of Earth, the winds are still strong enough to shake the spacecraft, picking up from about midnight through to early morning as cooler air rolls down from the highlands in the southern hemisphere and onto the Elysian Plutenia plains where the land is located. During the day, heating from the sun causes convective winds to build up, and these winds reach their peak in the late afternoon when atmospheric pressure drops and dust devil activity occurs. By evening, the winds have died down, and the conditions around the lander site become quiet. From late evening until midnight, the atmospheric conditions are so quiet, the seismometer is able to detect the rumblings from deeper inside the planet. All of the marsquakes have been detected during these quiet periods at night, but the geologic activity is likely to persist just as strongly during the day. The three biggest seismic events were all located in the Cerebus Fossae region, about 1,700 kilometres east of the spacecraft, where orbital observations have shown scientists boulders that may well have been shaken down cliffsides by seismic activity. Mars doesn't have tectonic plates like the Earth, but it does have volcanically active regions that can cause rumbles. In fact, there was one pair of quakes that was strongly linked to this region. Ancient floods in the area carved channels nearly 1,300 kilometres long. Lava then seeped through these channels within the last 10 million years or so, a blink of an eye in geologic terms. And some of these young lava flows show signs of having been fractured by quakes less than 2 million years ago. Matt Golombek from NASA's Jet Propulsion Laboratory in Pasadena, California, says it's just about the youngest tectonic feature on the red planet. It's basically a tectonic graben system caused by the weight of the Elysium Mons, the biggest volcano in the Elysian Planitia area. This all provides strong evidence that seismic activity on Mars isn't just a consequence of the planet cooling and contracting, but is also induced by tectonic stress. Meanwhile, another study has revealed that the Martian magnetic field at the landing site is some 10 times stronger than expected, and it fluctuates over timescales ranging from seconds to days. That study's lead author, Katherine Johnson from the University of British Columbia, says one of the biggest unknowns from previous satellite missions was what the magnetisation looked like over small areas. By placing the first ever magnetic sensor on the surface of the red planet, Johnson and colleagues have gained valuable new clues about the interior structure and upper atmosphere of Mars, helping them better understand how it and other planets like Mars formed. Before the InSight mission, the best estimates of the Martian magnetic fields came from satellites orbiting high above the red planet, and they were averaged over large distances of more than 150 kilometres. But the new ground-level data provides a far more sensitive picture of magnetisation over smaller areas and where it's coming from. In addition to showing that the magnetic field at the landing site was 10 times stronger than the satellites anticipated, the data also implied it was coming from a nearby source. Scientists have known that Mars once had an ancient global magnetic field billions of years ago. That magnetic field magnetised rocks on the planet. It switched off as the once molten Martian core began solidifying as the planet cooled down. And that turned off the geodynamo effect which generates the magnetic field. Because most of the rocks on the Martian surface are too young to have been magnetised by this ancient field, the study's authors think the field they detected must have been coming from deeper down, from much older rocks that are buried somewhere from less than 100 metres down to around 10 kilometres below the surface. The authors hope that by combining InSight's seismic and magnetic data results with satellite magnetic data and future studies of Martian rocks, they'll eventually be able to identify which rocks are carrying the magnetism and how old they are. The magnetic sensor has also provided new clues about phenomena occurring high in the upper atmosphere and in the space environment around Mars. Just like Earth, Mars is exposed to the solar wind, the stream of charged particles from the Sun that carries an interplanetary magnetic field with it and can cause disturbances like solar storms. But because Mars lacks a global magnetic field, it's less protected from space weather. The thing is, all previous observations of Mars have been from the top of its atmosphere at even higher altitudes, so scientists didn't know whether disturbances in the solar wind would propagate down to the surface, and that's important to know for future manned missions to the Red Planet. The sensor captured fluctuations in the magnetic field between day and night, as well as mysterious short-period pulsations around midnight, confirming that events in and above the upper atmosphere can be detected all the way down to the surface. The authors believe the day and nighttime fluctuations arise from a combination of how the solar wind and interplanetary magnetic field drape around the planet, charging the upper atmosphere and producing electrical currents, which in turn generate magnetic fields. It's an indirect picture of the atmospheric properties of Mars, how charged it becomes, and what currents are in the upper atmosphere. And as for those mysterious midnight pulsations, well, they're thought to be related to the solar wind's interaction with Mars, although scientists aren't really sure how. The InSight team are now hoping to observe the surface magnetic field at the same time as the MAVEN orbiter passes over InSight's location. That, you see, will allow them to compare data from the two spacecraft. You're listening to SpaceTime. Still to come, understanding the birth of atoms. And it looks like Betelgeuse has finally stopped dimming, at least for now. All that and much more still to come on SpaceTime. Scientists are about to begin a new study using new three-dimensional supercomputer simulations to recreate the evolution of different types of stars in order to better understand the origins of the universe's first atoms and elements. The Big Bang brought the universe into being some 13.82 billion years ago. But it took another 380,000 years for the cosmos to cool down enough from a turbulent quark-gluon plasma for protons and electrons to combine to form the first atoms of hydrogen and helium. The universe's first stars and galaxies were then created out of these first atoms. And it was these first stars which began the process of creating all the other elements we see today on the periodic table. The Australian National University is leading the new project to research the formation of these early elements. The work, using some $30 million in funding from the Australian Research Council, will be carried out at the new Castra 3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 dimensions, located at the ANU's Mount Stromlo facilities near Canberra. The project's lead scientist, Professor Lisa Curley from the ANU, says the research will help unlock how the universe formed its first matter in the dark moments after the Big Bang, how the first stars and galaxies formed and evolved into the universe we see today, and how the stars created the chemical elements in the universe. Castra 3D will involve more than 200 scientists from institutions across Australia and around the world, including astronomers, astrophysicists, engineers, and computer scientists. It'll help develop and use new high-technology instruments that will be crucial for the next generation of the world's giant optical telescopes and radio telescopes like the Square Kilometre Array. Curley says scientists will start using the locally developed 3D technology on existing optical and radio telescopes, building a picture of how galaxies formed and evolved across cosmic time. She says the technology will help scientists build 3D models which will pinpoint which materials formed in the early universe and map where those elements and stars were born and how they evolved into the universe we see today.
I guess 3D is a ARC Centre of Excellence, or All-Sky Astrophysics, and the goal of the centre is to understand our origins. So we're aiming to use Australia's biggest radio and optical telescopes combined with supercomputers to understand how the matter and the chemical elements in the universe formed and evolved across cosmic time.
I take it the way we currently see this is that the Big Bang itself created, when the universe cooled down enough from a quark-gluon plasma, created the first elements of hydrogen and helium and maybe a bit of lithium and beryllium too.
That's
and
right.
After that, the stars sort of took over that process.
That's right. And so this centre's aiming at these other elements, in particular the carbon and the nitrogen and the oxygen that are responsible for life on Earth.
And we think these are made either stars during their lifetimes, especially big stars. The population 3 stars, for example, would have been huge. They would have made huge amounts of these elements. And the other elements, the heavier elements, were made when these stars went supernova.
That's correct. So there's multiple stars that we need to look at, and we have detailed simulations of entire stellar populations where we have a big theory program in the Centre of Excellence where we're going to be generating whole populations of stars and then joining them together to create simulations of galaxies.
Are we looking at watching them evolve and see how they change with age through time?
Yeah, that's right. So in the simulations we can do that, and then with observations what we're going to be doing is we're going to be using the Milky Way to look at stars that formed at different times. We're going to be looking for the oldest stars in the Milky Way, which could be the first stars that formed in the universe, and also we're going to be then looking at the first galaxies that formed in the universe. We're going to be doing that directly with the James Webb Space Telescope, which is the next generation Hubble, and after that we'll be looking at galaxies at all different distances from us, and with that we can actually look back in time many billions of years.
James Webb's launching on an Ariane 5. It will look at the universe in primarily infrared because the light from the very early universe, which was ultraviolet when it left the stars, would have been stretched to infrared by redshifting. Tell me about what we hope to see there.
Yeah, so we hope to see the first galaxies when they were first forming. We've used the Hubble Space Telescope to look at very distant galaxies, and those galaxies look very different to the galaxies that we see today. So the distant galaxies in the very early universe were very clumpy and lumpy and very messy looking. They don't look anything like our beautiful spiral Milky Way galaxy or the elliptical smooth galaxies that we have around us. So we're hoping to look back even earlier to look at the building blocks of those galaxies, the smaller clumps of matter and the smaller clumps of star formation in the very early universe to see galaxies when they were actually first forming.
One of the big hopes of James Webb also, and I guess a dream for many astronomers, is to actually see a population 3 star.
Yes, that's right. So that's one of the hopes for this centre as well.
These population 3 stars, they're very different from the stars we see today, aren't they?
Oh, they are. They've got a very strange amount of elements in them. They're very pristine. They've got hardly any elements that we have around today in our Milky Way. So, for example, if you're looking at they're looking at the oxygen or the iron in them, they can have very, very little oxygen or iron.
When you have that sort of lack of metallicity, which is what we refer to when we talk about elements other than hydrogen and helium in the periodic table, when you have so little metallicity, that must make the star look very different. It must be a very different type of star to what we have today, in terms physically of size and mass.
We haven't found them quite yet. We've found stars that are very close, but not quite discovered those first stars.
Yeah, they're a real surprise. We've seen 2 really old stars, something like over 12 billion years old, and they're really plain-looking orange dwarfs. You look at them and spectral type K. You look at them and you wouldn't tell. That's right. And so we don't know what the stars that were formed even earlier, right after the universe was in the dark ages. We just don't know what they're going to look like. The galaxies looked very different back then when the universe was young.
Oh, they did. The galaxies were very messy. They were clumpy, and some of the galaxies were very, very blue compared to today. They had much more star formation. They had much more star formation happening per given volume than they do in galaxies today.
I think their figures are something like 30 times more than the Milky Way does now.
Yeah, it's enormous. And galaxies were also just forming their spiral arms several billion years ago as well. So back in the early universe, galaxies didn't have spiral arms. They just looked like tiny, lumpy things.
So the majestic spirals we think of when we think of the Milky Way, that wasn't there?
No, we think they formed around 6 to 7 billion years ago, but we are discovering galaxies with spiral arms that have already been cleanly formed around 6 or 7 billion years ago. So they must have started forming earlier, but we haven't seen any galaxies further back that have spiral arms.
And the other big question is galaxy clusters. Some of them are believed to have been formed very early on too.
Yeah, so galaxy clusters seem to have been formed many billions of years ago, maybe 8 or even 10 billion years ago the first clusters would have been forming. And we've been looking at some nearby, what we call nearby galaxy clusters. They're actually about 8 billion years ago. We look back in time, and we're both looking at we're understanding the star formation happening within the galaxy clusters, and also we're using them as gravitational lenses. The big galaxy clusters bend the light from background galaxies and magnify it and allow us to see the light from the background galaxies would be far too faint for us to see with our modern day telescopes. So the galaxy clusters are useful for many different reasons.
Is it fair to think that because the universe was a physically smaller place back then, hadn't spread out as much, hadn't expanded as much. That makes perfect sense that there would have been galaxy clusters so early on.
Yeah, so we think that galaxies were having lots more collisions and were much closer together in the past, and we think that that also contributed to the large amount of star formation that we see in the early universe. When galaxies collide together or pass close by each other, there's a lot of gas collisions happening within the galaxy. Their gravitational potentials are disrupted, and there's tidal forces, large tides occurring through the galaxies, and then this causes gas collisions, which then causes star formation to happen in the densest regions of the gas.
I take it you'll really be looking back almost to the time of reionisation.
Yeah, so part of this centre is to use the Murchison Widefield Array in Western Australia to actually detect the epoch of reionisation and ultimately to map it.
Why is reionisation important? What does that tell us about, well, the universe we live in today?
Yeah, reionisation's incredibly important because this was the time when the universe changed from being in the dark ages to the lit universe, when the first stars and the first galaxies and the first black holes lit up the universe. And it was basically a watershed event in the history of the universe. And it was the first time ionising radiation that rips electrons off atoms. It's the first time that was produced in the universe. And our current universe is 99% ionised, and how it got to this state is unknown. And that's one of the goals of this centre, to understand how this level of ionisation that we see today was reached across the evolution of the universe.
That's Professor Lisa Cooley from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Still to come, the Earth's new second moon. And later in the science report, growing fears that the COVID-19 coronavirus is about to be declared a global pandemic. All that and much more still to come on SpaceTime. Well, it seems weeks of speculation over whether the red supergiant star Betelgeuse is about to go supernova has finally been answered. And that answer is a firm no, at least for now. Until recently, Betelgeuse shone brilliantly as the ninth brightest star in the night sky. It was clearly visible with the unaided eye as one of the great guide stars, the brightest star in Orion, representing the scorpion's sting on Orion's shoulder. But it's been dimming at an unusually fast rate. And that's led to speculation that it could be about to explode as a core collapse supernova. Astronomers have been watching Betelgeuse dim and brighten over and over again for more than a century. Dimming is normal for semi-regular variable stars like Betelgeuse. But it's the rate of dimming during this latest episode, which has been so unusually rapid, which has led to all the speculation. Over the past 6 months, it's dimmed to the point where it's become the faintest it's been in over a century, and only half as bright as it usually is, dropping from 9th place to 21st place in terms of brightness of stars in the night sky. Now, new observations have confirmed that Betelgeuse has stopped dimming and is even starting to brighten again. Betelgeuse is located some 643 light-years away in the constellation Orion, which right now is in the northeastern sky. Calculations of its mass range from slightly under 10 to a little bit more than 20 times the mass of the Sun, and it usually has some 100,000 times the Sun's luminosity. Betelgeuse is so huge that were it located where the Sun is at the centre of our solar system, its surface would extend almost as far as the orbit of the planet Jupiter, engulfing the orbits of Mercury, Venus, Earth and Mars, as well as the main asteroid belt. Betelgeuse has a complex and tumultuous surface that frequently throws up impressive flares. It began its life as a blue giant about 10 million years ago. Astronomers think stars of Betelgeuse's mass usually only live for about 8 or 9 million years, meaning that it really is likely to go supernova any day now, which in astronomical terms could mean tomorrow, but it could just as easily mean 1 million years from now. See, high-mass stars like Betelgeuse burn through their nuclear fuel supplies really quickly, fusing hydrogen into helium in their core. Now, once all the hydrogen in the core's gone, gravity causes the star to contract. That increases pressure and temperature in the core until it becomes hot enough to ignite the helium there, fusing it into carbon and oxygen. At the same time, a shell of hydrogen starts fusing into helium around the core, providing additional fuel. Now, eventually the helium will run out, gravity will take over, causing the star to contract again, until pressures and temperatures increase enough for progressively heavier and heavier elements to fuse, until ultimately the star forms iron, which, no matter how massive a star is, it can't fuse into anything heavier, resulting in the end of nuclear fusion. That causes the star to begin rapidly dimming, while at the same time, gravity starts collapsing the star down, triggering a supernova explosion. And that's the reason why so many people were getting excited about what's been happening. You see, when Betelgeuse does explode, it'll temporarily outshine all the other stars in our galaxy, easily outshining the Moon, and it will be clearly visible in the daytime sky from Earth. So, what caused all the dimming in the first place? Well, it could have been just a big dust cloud ejected by Betelgeuse towards the Earth, affecting its brightness as seen from here. Or it could be that its stellar surface has cooled for some mysterious reason, although scientists don't know exactly what that reason would be. But we can say for certain that based on Betelgeuse's past dimming and brightening patterns, it appears to cycle in brightness through two co-occurring patterns. There's a short period cycle lasting 425 days and a longer cycle lasting around 6 years. And it looks like that over the past 6 months, these two separate cycles began to sync up. So you have the two separate lots of dimming occurring at the same time. And that would explain what we've seen happening. It would also explain that now that these cycles are moving out of sync, Betelgeuse is again getting brighter. You're listening to SpaceTime. Coming up next, the Earth's new second moon. And later in the science report, new studies confirm that Australia's devastating bushfire catastrophe burnt out over 21% of all Australian forests. All that and more still to come on SpaceTime. Planet Earth has a new moon. That's in addition to our regular 3,475 kilometre wide moon Luna, which is orbiting some 384,400 kilometres away. The new cosmic interloper, officially catalogued as 2020 CD3, is on a highly elongated looping 47 Earth-day orbit, wrapping around both the Earth and extending far out beyond Luna. 2020 CD3 is between 1.9 and 3.5 metres wide, about the size of a small car. And no, scientists don't think it was Elon Musk's Tesla. A space rock was discovered by the University of Arizona's Catalina Sky Survey at the Mount Lemmon Observatory on February the 15th. And follow-up observations from 6 other telescopes around the globe confirm that the object is orbiting the Earth, at least for the moment. Interestingly, the simulations also suggest that it's been orbiting the Earth for at least 3 years. However, those same simulations are also suggesting that 2020 CD3's orbit isn't stable, and it will likely be gravitationally flung out of Earth's orbit next month. However, there are several different simulations of its trajectory, and they don't all agree. So more observations will be needed before astronomers can be sure. The one thing they are sure of is that 2020 CD3 is definitely a temporary moon. It's not a piece of space debris. The Minor Planet Center is classifying 2020 CD3 as an Amor asteroid since it orbits beyond Earth. However, NASA's Jet Propulsion Laboratory in Pasadena, California, considers it to be part of the Earth-crossing Apollo group of asteroids instead. Whatever its origins, the space rock is a passing asteroid that simply got too close and was captured by Earth's gravitational field. There are literally millions of asteroids and meteors orbiting the Sun in the vicinity of the Earth, and every now and then one of them gets caught up in Earth's gravitational field and ends up going into orbit around our planet for a while. However, 2020 CD3 is only the second confirmed space rock to be discovered orbiting the Earth. The first was 2006 RH120, which was captured by Earth's gravity in June 2006 and stayed until it was finally flung out of orbit around September 2007. It was also discovered by the Catalina Sky Survey. Another potential mini-Earth moon was 469219 Kamaolwa, which was discovered in April 2016. As it orbits the Sun, it appears to circle around the Earth as well. But it's too distant to be a true satellite of Earth, and instead is best described as the most stable example of a quasi-satellite, a type of near-Earth object, or NEO. And it's not alone. Lots of other space rocks have shown up over the years, but usually end up appearing to orbit a point other than the Earth itself. A good example of that would be the NEO asteroid 3753 Cruithne, which looks like it's on a weird horseshoe-shaped orbit around the Earth, but is actually orbiting the Sun with the Earth in a one-to-one resonance. Of course, Earth also has the occasional Trojan asteroid, such as the 300-metre-wide 2010 TK7. These Trojan asteroids are NEOs which orbit the Sun on the same orbital path as the Earth in stable gravitational sweet spots known as the Lagrange L4 and L5 positions, located some 60 degrees behind and ahead of Earth's orbital track around the Sun. Large dust clouds known as the Kowalski clouds are also observed at these locations. And there are lots of other small asteroids and meteoroids orbiting the Sun, which also occasionally enter orbit around the Earth for short periods of time, becoming temporary natural satellites. It's all just a question of finding them. This is SpaceTime. SpaceX has launched another batch of 60 Starlink satellites. This latest flight from Space Launch Complex 40 at the Cape Canaveral Air Force Station in Florida brings to 300 the number of Starlink Internet satellites now in orbit. Bad weather conditions and an issue with an upper stage valve had delayed the mission by a day, and this may have been somewhat of an omen for things to come, with the Falcon 9 booster failing to land back on its drone ship Of Course I Still Love You, which had been pre-positioned downrange in the North Atlantic Ocean. Instead, it splashed down in the water nearby.
The vehicle, satellites, weather, and range are all looking good for an on-time liftoff.
Falcon 9 startup.
LD is go for launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition, liftoff.
Falcon 9 pushing down range. Power and telemetry nominal.
It is T plus 47 seconds, and we have just had liftoff of our Falcon 9 vehicle, taking our Starlink payload to its targeted orbit. In about 15 seconds or so, we will be passing through max Q. Max Q is the maximum aerodynamic pressure that the vehicle will see throughout its
Falcon 9
ascent.
supersonic. Falcon 9 is experiencing maximum aerodynamic pressure.
And there's that call out for max Q. Coming up next will be 3 events happening in rapid succession, the first of which will be MECO, or main engine cutoff, followed immediately by stage separation, and this is where the first stage separates from the second stage, and then followed by SES-1, or second engine start 1.
MVAC engine chill.
Today we will only be having one burn of the second stage.
MECO.
Stage separation confirmed.
And there we've just had MECO, main engine cutoff, and stage separation.
MVAC ignition.
And second engine start 1. That engine is starting up and should be turning bright red shortly. Now coming up in about 5 seconds, we will have fairing deploy.
Fairing separation confirmed.
And there is fairing deploy. Now both fairing halves are making their way back to Earth. Let's hope that we can catch both of them today on Mystery and Mischief.
Okay, stage 2 continues to burn nominally with those 60 Starlink satellites up on top, while stage 1 begins its descent down to the drone ship. So coming up very soon, we're going to have a few events on stage 1. The first is the entry burn. That's coming at about T plus 6 minutes and 48 seconds or so. That's where 3 of the M1D engines are going to reignite, and what they do is they slow the first stage down as it re-enters the upper part of the Earth's atmosphere. That burn's going to go for about 20 seconds until you hear the call out, stage 1 entry burn end. About a minute and a half after the conclusion of that entry burn will be the landing burn. Now that's where we reignite the center E9 engine on the bottom of Falcon 9 on that first stage. And what that does is then slows the vehicle down to 0 velocity as those landing legs are deploying and hopefully placing this stage on the drone ship for the 4th time and hopefully marking the 50th successful landing of a Falcon 9 booster. Stage 2 trajectory continues to be nominal. We're hearing that MVAC power is good and everything is looking really awesome. Stage 2 is burning with more than 210,000 pounds of thrust. And the 60 satellites that are on top of that second stage are going to join the previous batches of Starlink satellites already in orbit, further filling in our constellation, which gets us another step closer to providing high-speed, low-latency internet access, targeting places where broadband connectivity options like fiber are too expensive or unreliable or even sometimes completely unavailable.
Stage 1 FTS is saved.
Stage 1 entry burn is started. Fairing vessels have AOS, and stage 1 entry burn is shut down.
All right, and as you just heard, that entry burn has concluded, and I'm also hearing that it was a pretty good one. So coming up
First
next,
stage LOS expected.
Coming up next for stage 1, in just under a minute, is going to be the start of the landing burn. This will be, if successful, the 50th successful landing of a Falcon booster, not necessarily a Falcon 9. We've landed boosters for Falcon Heavy as well, and this counts as one of those. Okay, we're a little over 10 seconds away from that landing burn start. Meanwhile, stage 2 continues
Stage
to
2 is
perform
after
nominally.
terminal guidance.
Stage 1 landing burn is started. Landing legs have deployed. MVAC shut down.
Okay, we were
Stage 2
expecting
FTS is saved.
we were expecting the call out for landing, and we obviously didn't see it there on the drone ship. So let's look back at stage 2.
Newfoundland AOS.
And we clearly did not make the landing this time. However, stage 2, we have confirmed SECO, which is second engine cutoff. Let's listen for the call out of the orbit.
Cape LOS expected.
And we have a good
Nominal orbital
orbit.
insertion of stage 2.
All right, now stage 2 is going to coast in this orbit for a few minutes, and during this time it'll start to spin along its central axis, which gives the Starlink satellites the momentum that they need to space themselves out over time after they deploy.
The booster used for this mission had previously launched the CRS-17 and 18 Dragon cargo ships to the International Space Station. That was back in May and July of last year. And it also launched the JCSat-18 Pacific-1 mission back in December last year. Attempts to retrieve the two halves of the payload fairings with nets aboard the recovery vessels Mistree and Mischief were also unsuccessful. The 260-kilogram broadband internet Starlink satellites were deployed into an initial 212 by 386-kilometre high orbit. They'll use their own onboard propulsion systems to gradually raise their orbits to an operational altitude of 550 kilometres in 3 separate orbital planes. A Chinese Long March 2D rocket has carried what Beijing are calling 4 new technology test satellites into orbit. The spacecraft, named JSW-C, D, E and F, were flown from the Jiaqiang Satellite Launch Center in southwestern China's Sichuan province. Beijing claims the probes will be used to test new Earth observation technologies. And time now to take a brief look at some of the other stories making news in science this week with a science report. The Australian government is activating its emergency plan and extending travel bans amid growing fears that the COVID-19 coronavirus is about to be declared a global pandemic. There are now some 90,000 confirmed cases of COVID-19 in 40 countries, with more than 3,000 deaths reported so far. Australian Prime Minister Scott Morrison says there's now every indication that the world will soon enter a pandemic phase. The latest World Health Organization situational report indicates a 3% mortality rate in China for the disease. A further 5% of those infected have needed intensive care, and another 14% needed hospitalization. Morrison says the scope of Canberra's emergency response will be escalated depending on the spread of the illness. In the worst-case scenario, it would include cancelling large gatherings such as sporting events, closing schools, having people work from home, suspending elective surgery, increasing the capacity of intensive care units, locking down aged care homes, closing childcare facilities, and prioritising mortuary services. Japan has already announced the closure of all its schools, and Saudi Arabia has suspended the entry of all foreigners. Professor Raina McIntyre from the Biosecurity Program at the University of New South Wales says sustained transmission in Australia could result in anywhere from 25 to 70% of the population getting infected. McIntyre says that based on the Chinese numbers, if 50% of Australians became infected, it would mean up to 400,000 people dying, 650,000 needing intensive care, and almost 2 million people needing a hospital bed. A series of scientific studies looking at Australia's devastating bushfire catastrophe has found that more than 21% of Australian forests were burnt out in the wildfires. The findings, reported in the journal Nature Climate Change, showed that the fires were also unprecedented, standing out far beyond any other bushfire season ever recorded in Australia. Scientists found there was no doubt that the record temperatures of the past year, which dried up the landscape and supercharged the blazes, would not have been possible without anthropogenic climate change. Researchers found that while the influence of human-caused global warming on the droughts and fires in Australia is hard to disentangle from natural climate variability, human-caused climate change amplified the extreme heat waves observed during the summer. The wildfires blackened some 200,000 square kilometres, killing over 1 billion animals, with some endangered species driven to extinction. The fires also killed at least 34 people and destroyed almost 6,000 buildings, including some 2,800 homes. The report warns that under a scenario where greenhouse gas emissions continue to grow, the 2019-2020 season could eventually be considered average by 2040 and even exceptionally cool by 2060. Does the tendency to have boys or girls run in families? Well, by examining the entire population born in Sweden since 1932, that's over 3.5 million parents producing some 4.7 million children, researchers have concluded that no, they do not. Reporting in the journal Proceedings B, scientists found individuals do not have an innate tendency to have kids of one gender or the other. Rather, the chances of having a boy or a girl is essentially random, though there are slightly more male births in general. Scientists have discovered giant bacteriophages which blur the lines between viruses and bacteria. Bacteriophages are viruses that infect bacteria. Like other viruses, they were considered distinct from cellular life, owing to their inability to carry out most biological processes required for reproduction. Typically, bacteriophages, like all other viruses, have small genomes and depend on their hosts for replication. But now, a report in the journal Nature claims scientists have discovered 351 new species of bacteriophages with giant genomes and capabilities normally associated with bacteria. The giant bacteriophages were identified by scouring a large database of DNA generated from nearly 30 different Earth environments, ranging from the intestinal microbiome of premature infants and pregnant women through to a Tibetan hot spring, a South African bioreactor, hospital rooms, oceans and lakes, and even deep underground. The 351 bacteriophages identified by researchers all had genomes that were more than 200,000 base pairs long. That's 4 times the average phage genome length of 50,000 base pairs. Among these was the largest bacteriophage discovered so far. Its genome was some 735,000 base pairs long, nearly 15 times larger than the average phage. That's not only the largest known phage genome, it's also much bigger than the genomes of many bacteria. While most of the genes code for unknown proteins, some were identified as coding for ribosomes, which translate messenger RNA into protein. And these genes aren't typically found in viruses, only in bacteria and archaea. A new study has found that Neanderthals and modern humans diverged at least 800,000 years ago. That's substantially earlier than most DNA-based estimates. A report of the journal Science Advances analysed dental evolutionary rates across different hominin species, focusing on early Neanderthals. Ancient DNA analysis has generally indicated that both lineages diverged around 300,000 to 500,000 years ago, and that strongly influenced the interpretation of the hominin fossil record. But the new study found the teeth of hominin ancestors of the Neanderthals diverged from modern human lineage much earlier than previously assumed. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free twice-weekly podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favourite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.